It's my real pleasure today to introduce Kayla. So Kayla did her PhD in Cambridge. She defended in 2014. And then she was a postdoc, NSF postdoc fellow at USGS, where she worked in quantifying the volatiles in magma. And part of this work was actually conducting field work on a volcano that I'm not going to pronounce the name, but that's located actually at the boundary between North Korea and China. And then after that, she did a postdoc at ASU, starting experimental petrology work. And since 2019, she actually joined the NASA Space Center. We talked about the organization of these centers and how it's linked to the private company Jacobs during meet and greet, and it's fascinating actually. So if you have questions about that, you should probably send her an email and ask her. And so she's doing a lot of she's using a lot of different techniques. She's doing a lot of field work, but also experimental work, geochemical analysis, and geochemical thermodynamic modeling, basically. So she's combining all that to study the cycle of volatile on Earth. She is doing a lot of research about that. And now that she's at NASA, she will progressively do more and more extraterrestrial work, basically. So that's one thing. So the first time I actually heard about Kayla was because she's actually the first woman conducting fieldwork in North Korea, and just for that, it's kind of remarkable. So that's the first time I heard her name actually. And the second time I heard her name is when I was at Cardiff in UK, so three years ago actually, and I needed to do some experiments using San Carlos olivine. And I sent an email to the experimental petrologist community, and we actually never met before, and Kayla directly answered. So I sent an email to have information on how to acquire such olivine, and Kayla directly answered my email very, very nicely. She was a postdoc at ASU at this point, and she just said, well, I'm going to go to San Carlos next weekend, collect some olivine for you and ship them in UK. So I thought it was a very nice move, and thank you again for that. Those olivine are actually back in Utah now, and I'm using them in experiments right now. So thanks again for that, and yeah, and it's you.
All right. Well, hey, thank you so much for the invitation and for that introduction. Yeah, and I also have to thank you for tasking me or tasking people with getting you some olivines, because I wanted to go out there anyway. And because of the date that I went out, it happened to be a super bloom of California poppies, which are these really bright orange flowers that were just covering the landscape in San Carlos. It's a super bloom like I've never seen before and haven't seen since. And in fact, there were people, it's on the Apache Indian Reservation, the location of San Carlos, and there were a lot of members of the reservation out there doing photo shoots. I think there was a woman taking like her wedding photos, because it was absolutely gorgeous. So that was a really cool thing that I got to see because of that. And I'm glad to know that those crystals were useful. So today, I'm going to be talking to you guys about some of my work focus on thermodynamic modeling to link what we know about the subsurface beneath volcanoes with what we know and what we can measure at the surface of volcanoes, specifically with respect to volcanic degassing. So that's the big question is there at the top, what drives volcanic eruptions? And I'm gonna be talking a bit about, well, actually, I'll just go ahead and let you see what I'm gonna be talking about by actually giving the presentation. Let's do that. All right, so I wanted to start off with just an overview of the evolution of volcanic gas monitoring throughout the decades. You can see here in the upper right, the classic collection of hand samples of the volcanic gases and things like gigabach bottles, all the way up through more and more increasingly technological techniques, remote sensing, all the way down to here on the bottom right, we have a drone outfitted with a number of sensors that can be flown through a volcanic plume. And the point of putting this up here is just to say that we've gotten to the point in the field where we are capable of collecting large amounts of data and really high quality data sets, all different types of, all different chemicals within the gases. We can detect more things. We can make more measurements and real-time measurements. In a lot of cases on volcanoes that are well instrumented, we have real-time telemetered data from multiple gas monitoring stations. So we're at the point where we have this wealth of data, and sort of what I feel like my job, or what I can contribute to that, is making better tools to quantitatively evaluate those data so that we can say something meaningful about the volcanic processes that are giving rise to the things that we're measuring at the surface, namely the gases. So I'm going to start with a kind of an overview of how we've always used gas compositions as this geochemical fingerprint of magmatic processes at depth. And we've been doing this for a very long time. This plot on the left is showing you, hopefully you can see my cursor, is showing you pressure in bars. So this is deep coming up to the surface, and the mole fraction of each of these species within the gas and how that changes with pressure. So we can see immediately from this that SO2, the most commonly measured gas at volcanoes, degasses relatively shallowly. It's not very abundant in the gas until more shallow pressures. H2S is similar. It also degasses relatively shallowly. Carbon dioxide and carbon monoxide degas very deep. So deep gas is going to be dominated by CO2 and pour into H2S, SO2. Another important thing at some volcanoes that have hydrothermal activity is whether or not that hydrothermal activity is present and influencing the gases. You can determine that by looking at things like H2S, SO2 ratio, because H2S will be unaffected by this hydrothermal activity, whereas SO2 is soluble in water, and so it will be taken out of the gases before it reaches the surface. So for a long time, we've used these kinds of properties of these gases to say, oh, we think the ratio of these gases is changing, therefore the depth of the magma that's supplying these gases is changing. And I want to say, okay, how can we be more quantitative about this with everything that we know about? We know a lot about the thermodynamics of these gases. What can we pull from the petrology to make a stronger quantitative link? So one of the main problems in this case is applying this to any volcano that we might want to is, number one, every volcano is not the same. And so quantitatively, it's difficult to come up with this general model that says, this change in gas signature equals this change in the magma system. And we don't know a lot about the details of how volcanoes are different from one another, which presents another challenge. And so this is sort of what I want you to keep in the back of your mind as I give this talk. What I'm going to be talking to you about is a specific example of how we might approach this problem with a specific eruption. But really, this is done in service of the very, very, very early stages of a broader vision for a generalized tool that can do these kind of quantitative analyses with the gas data and the petrological data that we have. And this is just an overview of what I think that kind of a model should look like, what we might want out of that kind of a model, and things that we can do to that model that would make it even possibly predictive. And so I'm not going to go into these in detail, but just to say, we can leverage what we know about thermodynamics so that it can be thermodynamically based. So it's fundamentally based in numerical methods. We can use existing modeling strategies and incorporate those into a model that's capable of doing more. We can work to facilitate connections between disparate systems and disparate data types. That has been a challenge. Using something like Python, it just happens to be my language of choice, but that's a great way to build an accessible infrastructure of a model. We want it to be usable at all levels. So one of the key things here is that we want fundamental researchers to be able to use this tool to make groundbreaking discoveries, but we also want people at observatories who have limited time, limited resources. We want them to be able to use that kind of a tool to make not only responsive, but the holy grail would be to have a model that gives you some kind of predictive capability in terms of what a volcano might do. So with that in mind, and again, this is, like I said, sort of a very, very early incarnation of this idea of this sort of generalized model. I'm going to show you a specific example of one of the ways that we can start to think about how do we apply these techniques to an eruption that occurred at Poas volcano in Costa Rica. So here on the right is a map showing Costa Rica and the location of Poas. It's a subduction-related volcano. This is an image of the crater, and you can see this beautiful lagoon here, this aqua-colored lagoon, which is a very acidic lake, and some fumarolic degassing that happens here. Now, POAS is known to have relatively frequent small, medium, and large-sized phreatic eruptions that can, at times, completely evacuate that lake that you saw. And such was the case in 2017, where there was a large eruption that occurred and totally evacuated the lake. So to give you some context here, that picture on the left that you're going to see is going to be a zoom in looking straight down at this part of the lake, this sort of shoreline. So this here.
May I interrupt you? We don't see your cursor actually.
Oh, okay. Sorry about that. I will just describe what I'm pointing to. Thanks for letting me know. Okay, so you can see that sort of reddish mountain in the center of the image, and then on the right-hand side, that shoreline of the lake is the same shoreline that you're seeing in this image on the left. But as you can see, there's no water in the lake. It was completely evacuated when the eruption occurred. This was a pretty big phreatic eruption, and I highlighted two things here. This is in red, the main vent where we're seeing an ashy eruption, and in yellow, this yellow arrow is showing the secondary vent that was revealed due to the evacuation of the lake with this canary yellow cone and plume. Here on the right, these four images here, the top left one is a picture of that little cone. And you can see it's just, as you might imagine, entirely made out of sulfur. It's a very, very sulfur-rich cone, sulfur-rich gas plume. And in fact, all of the images here that I'm showing you on the right are the collection of sulfur flows and other sulfur deposits from this eruption. So we can say immediately this is a very, very sulfur-rich eruption, just from looking at this. So let's also then take a look at the gas data from that eruption. What I'm showing you on the left are two measurements of the gas. And note the time scale here, this goes all the way back to 2013 on the left of the plot, all the way to almost to this year on the right. So it's a lot of data. The top plot is the SO2-CO2 ratio. So again, that's sort of our proxy for depth. SO2 is a shallow degasser and CO2 is the deep degasser. And on the bottom is the H2S-SO2 ratio. And I've highlighted a few regions here. So before and after the eruption, I'm calling a passive phase, just meaning this is sort of background what POAS does when it's degassing, or typical gas signature. Then we have this run-up phase shown in the pink, where we see this precipitous drop-off in SO2-CO2 and increase in H2O-SO2. And that occurs just leading up to this eruption, where that behavior completely flips and does a 180. And we see extremely high, so the eruption is marked in this red line, extremely high SO2-CO2 ratios and extremely low H2S-SO2 ratios. So the eruption is also shown on the right-hand side plot, which is showing you the SO2 flux, so the amount of SO2 coming out in tons per day. And during where that red line is, like at the point of that initial part of the eruption, we recorded 1,500 tons per day sulfur SO2 at POAS, which is the highest sulfur flux ever recorded at POAS, which is pretty substantial because POAS is known to be a sulfur-rich volcano. So, we have a couple of questions here, which is, first of all, can magma degassing account for this extreme sulfur-rich signature? How do you extract that much sulfur out of a magma? What does it take to do that? And then the second question being related to that, what triggered this eruption? We have this run-up period up to the eruption. What was happening in the magmatic system leading up to that catastrophic release of all this sulfur? So this is, I'm going to give you an overview of the modeling strategy that we use to try and answer these questions. And the modeling strategy we're going to use is adopted from a different volcano, shown here on the left, Erebus volcano in Antarctica. And this was chosen because there was a model created to link petrology and surface gas chemistry at Erebus, in large part because it's an extremely well-constrained system. We have excellent gas measurements, as we do at POAS. We have melt inclusions from depths throughout the plumbing system going down to the moho. We have, numerous studies on the mineralogy, this, seismicity, infrasound, almost everything you can imagine. It's a very, very well studied volcano, and so we know a lot about it. And so this model was developed to say we know a lot about the stuff that's, goes into the model, the stuff that's in the subsurface. We know about the stuff that's coming out of the model, and if you're doing a forward model, the stuff that's coming out of the top. So we can use these two well-defined endpoints to then find the link in between those two endpoints, namely, what are the thermodynamic parameters shown in this big circle here? What are the thermodynamic parameters that link these two different systems? So I'm going to briefly go into what the things that model considers and how it links these two systems. And again, this is all in terms of the gas. So for a model like this, where we want to recreate exactly what the volcano is doing from bottom to top, the holy grail for us is to quantify the quote-unquote gas budget. That means, can we determine all possible sources of gas that are contributing to what comes out the top? And what this is kind of showing you here schematically with these little dots, they represent the different regions, which I've labeled in the picture on the left: deep, intermediate, shallow, and lava lake. You can imagine that gases associated with each of those regions should add up to the gases that we see at the surface. And here, for the purposes of this talk, we're concentrating only on the gas/fluid portion of the magma, so not considering, say, breakdown of solid phases or uptake of volatile components by a solid phase. And there are multiple different ways you can get gas out of these different regions. And the first is simple degassing. So what I'm showing you here are 3 sources of gas in the subsurface that are created by the ascent and degassing of melts. So at Erebus, we know that melts are stored at each of these locations shown here, again, shallow, lava lake, shallow, intermediate, and deep. And you can imagine when a blob of magma moves from that deep magma into the intermediate magma, it evolves, it changes its composition, and due to the pressure drop, it's going to release some volatiles. You can account for that degassing that's occurring by looking at melt inclusions, which are trapping the dissolved volatiles within a melt at the moment that they're entrapped within a crystal. We can look at a melt inclusion from, for example, the deep reservoir. We can look at a melt inclusion from, for example, the intermediate reservoir. And the difference between the volatile content of those melt inclusions is the amount of gas that would have been released during that ascent step. So you can see 3 regions, 1, 2, and 3 labeled here that represent the degassing from those steps. But we also have 4 more regions to account for. So that was just the sort of the degassing of those melts as they're moving from A to B to C. But what about any fluid that's coexisting and just hanging out happily at equilibrium in any of those reservoirs? So within the magma at depth in the intermediate regions, the shallow region, the lava lake region. And the way that we come up with quantitative values for these is using this thermodynamic model. I hate putting a lot of words on my slide, and so I apologize for all of the words and fancy looking Fs on this slide. But if I had had a picture that could represent oxygen fugacity, I would have chosen it. So let me know if you have better suggestions for how I might schematically represent sulfur fugacity and the like. But joking aside, this is so our first set of 3 gases, right, is degassing between the regions, and the last set of gases, which are these 4, 5, 6, and 7, are these what I'm calling equilibrium fluids. So again, just fluid that's hanging out in each of these reservoirs. So this represents the gases that are stored at depth, because any of those could at any time move upwards and leave the surface of the volcano. So once we've calculated all of our 7 different gas compositions from each of these regions, we want to think about what would happen to those gases if we took them from their place of storage or place of origin and decompressed them and brought them to the surface to 1 bar. The bulk composition of those gases is not going to change, but the speciation within those gases for example, the oxidation state of sulfur, whether it's in the SO2 phase or the H2S phase. That's going to change because that's pressure dependent. And so what I'm showing you here is just an example using a model that's very similar to the model that I created. And we're going to start with some fluid that's hanging out here in the intermediate region. And on the left, on this plot here, you see pressure in bar going from deep to shallow, shallow on the right. And then again, it's similar to that first plot I showed you, the gas molar fraction. And each of those gases are represented by those colored lines. And as we move our gas to the surface, we can see that the speciation of those gases change. So that's just another step that we have to consider. This is a mathematical representation of what I just said, if you're sort of mathematically minded. Again, like I said, we know that the bulk composition of the fluid won't change, but we can do some math to explain how the speciation of each of those gases will change. So now that we've done that, we've calculated all 7 of our gases at depth, we've decompressed them all to the surface. We know that if we can say that we think we've accounted for every possible contribution, every possible fluid that's contributing to our surface degassing, then some combination of those 7 fluids has to add up to what we measure at the surface gas. And we can do that with a very simple mixing model. And what I'm showing you here is exactly the model that we use, and it is very, very simplistic. We're just sort of adding a proportional factor to each of our fluids. So this G sub I is the concentration of each of the gas species. So let's pick SO2. So it'd be the concentration of SO2 as measured in our surface gas. And we know that should equal the sum of the concentration of SO2 in each of our contributing fluids times some proportional contribution, right, from 0 to 1 or from 0 to 100 of the total. Now this is exactly what I just showed you, but it is a visual representation of that rather than a mathematical one. And this is a ternary diagram showing gas compositions where we have SO2, S total cut off here at 40 mole%. On the left is CO2, and on the right apex is H2O. The big yellow dot represents our measured surface gas at Erebus. These colored squares represent the degassing, so that's the differencing of the melt inclusions. And the colored dots on the left represent those equilibrium fluids that are hanging out in each one of those magma storage regions. Yeah, so that's shown there. And you can kind of imagine, if you've ever thought about mixing models, you can, and I like to apologize for this plot because this is like the most petrology plot ever. We love ternary diagrams and we love tie lines. So you can imagine some tie lines connecting various points here, sort of the left, the colored dots pulling that composition to the left and the squares pulling that composition to the right, with the length of that tie line representing its proportional contribution to the total. And so we can run this model and say, within some error, let's say within 2 mole%, give me all possible combinations of these different gases that equal the surface gas, again, within some error, within, for example, 2 mole%. And when we do that and we run our model a bunch of times, in this case, we came up with, I think it was 143 or something like that, total model outputs that match these conditions. So here on the bottom of this plot, you see model output number. And then the way to read this plot, all of the colors correspond to the different regions, both in terms of their equilibrium fluid and their degassing fluid. And each slice of this plot vertically represents one model result that could satisfy our conditions, and the conditions are that has to match the surface gas. And so in this case, at Erebus, we could say that throughout, for every one of these cases, you can see this huge contribution from this light gray fluid. More than 60% of the fluid is derived from this deep degassing source. A huge proportion of the fluid is always derived from the lava lake equilibrium fluid. And there's more or less influence from our shallow equilibrium fluid and our intermediate equilibrium fluid, depending on which model result you pull from. But that gives us a good indication that this system is controlled largely by its deepest part, and it's subsequently secondarily metered by the activity in the most shallow part of the system. So that's all. Oh, and this is just another picture to remind you of where those gases kind of started. And so that's all well and good for Erebus, which, like I said, is super well constrained. But we want to be able to make this more generalized model. So where can we start? And a place like POAS is a great place to start because we have no melt inclusion data. We have very little geochemical data. There is a hydrothermal system which affects our gases in a way that wasn't taken into account by that model. But we do have fantastic gas data. So we know almost nothing about the subsurface, but we have great gas data. So now that we have this model established, the approach for POAS will be to take a really wide range of input parameters, wide range of pressures, temperatures, oxygen fugacities, even volatile contents, put them into our model and see all of the possible gases that can come out of this model. And here's a schematic example of what I mean by that. So again, remember our question being here, can magmatic processes alone account for that sulfur signal we saw? So another way to put that is, can we identify magmatic gas signatures within the POAS data? And what I'm showing you here is just this conceptual diagram or whatever XY space you like, compositional space, of all possible gas compositions in the universe. No constraints whatsoever applied here. Some finite set of all the gas compositions in the universe. And on top of that, we can say, okay, let's run this model with, here in the gray box on the right, I'm showing an example of some range of parameters we might input into our model. Let's say it can't go above 2,000 bars, the depth of the degassing. The temperature is going to be around 1,000 C. We can vary that as much as we like as well. And the H2O, CO2, and sulfur concentrations in the magma can vary between these values shown here. And we can vary this as much as we like and come up with then these green triangles, which are all possible feasible magmatic gas compositions based on that range of inputs. And then to answer our question about magmatic gas signatures in the data, in the natural data, we can compare our feasible synthetic gases to the actual measured surface gas data, and where those things overlap, that tells us that that measurement is possibly from a magma. If you set these conditions, again, these conditions in the gray box here to the right, if you can set that range of input parameters wide enough, then any surface gas data measurement, any of these red pluses that doesn't overlap with the green triangle, there's no way it could be created by the magma. So how do we pick these range of parameters? Step one is petrologize, my favorite thing to do. And again, like I said, at POAS, we don't know much. This is the case for a lot of even very well-instrumented volcanoes like POAS around the world. But we can make some inferences. We know something about what arc magmas look like. We know something about what other magmas in Central America look like. So this is an example showing pressure temperature conditions from some similar-ish lavas from Mexico, also arc-related. And what you're seeing here are regions where certain crystals are stable depending on the pressure and the temperature. And now we know the crystals that are within the POAS magma. We know that there's olivine, augite, and plagioclase. And so that puts us somewhere in this blue triangle. We can get a little bit more constrained even if we want, because we do know that the plagioclase from POAS have high anorthite content, which indicates that they're going to have higher H2O concentrations in the coexisting melt. And so we're probably somewhere in this red triangle. So that gives us sort of a pressure window and a temperature window to be working in. Now, how do we come up with what possible volatile concentrations might be in the magmas at depth? We know nothing about, we haven't measured that at POAS, but we can look to, again, nearby volcanoes or other arc-related volcanoes and set a huge range. So we know that at the pressure range that we've picked, our saturation is around 5 weight%. We're going to give ourselves a little bit of buffer and say we're going to allow the water concentrations at depth to range from 2 to 6 weight%. Similarly for CO2, nearby volcanoes, have 50 to 300 ppm CO2, but arcs can have up to 1,000 ppm CO2 in them. So we're going to just go crazy, and we're going to say 300 to 3,000 ppm CO2. And similarly for sulfur, nearby volcanoes, I think this number is from RNL, can have up to 3,000 ppm sulfur. We know Poas is pretty sulfur rich. We're going to go all the way from 300 to 5,000 ppm sulfur. And then we're going to do exactly what we did for the Erebus case, where we can come up with a range of these different bulk compositions, use our model. This is essentially what the model is doing. This is the bulk of that model. It's taking our bulk compositions and speciating them at given pressures, temperatures, and oxygen fugacities. So we do that for these fake Poas gases, for a range of pressures, temperatures, and oxygen fugacities, degas them to 1 bar, and calculate synthetic gas compositions. This is a few plots showing all of the gas compositions that we calculated using those constraints that I showed you a couple slides ago. And again, this represents all possible magmatic gases from this shallow Poas system. What I'm showing you here, the y-axis of all of these plots is the SO2-CO2 ratio. So that would correspond directly to something we might measure in the gas at the surface. And then on the x-axes are dissolved H2O, CO2, and sulfur concentrations from left to right in the melt that produced those gases. So I don't need to go into detail about these here, but just to sort of show you that there's a spread of possible gas compositions that we come up with, and that it's not just a uniform square of values. There is some shape to the space of possible values that we have. So maybe we have some hope in using that to suss out magmatic signatures. So let's go ahead and dive into some of the results, starting again with this plot that I showed you at the beginning of the talk. It's the same data I'm showing you here, and just once again, where these dots are measured, gases measured in the field, and once again, sort of pointing out this run-up period where you have these purple arrows, precipitous change in the gas ratios leading up to the eruption, and then a 180 flip of those ratios during the eruption, settling back down to our typical values after the eruption. I've also shown, once again, this SO2 flux plot on the right here. And I just wanted to point out that just before the eruption itself, so in this point where SO2-CO2 was at its lowest and H2S-SO2 was at its highest, the sulfur flux, the actual sulfur that was coming out that was being measured, was below the detection limit. So it got low enough. Basically, our SO2 was just dropping and dropping and dropping until it was immeasurable. And then we had this explosion where right after that is where we got these high values in these green triangles of 1,500 tons per day sulfur. Okay, so on top of this, I'm going to overlay our results from our modeling. So what you're seeing here in the yellow dots with the red outlines, those are all of our synthetic gases that matched any of the measured gases. And it's worth noting that to be considered a match, our gas had to match both in terms of SO2-CO2 and H2S-SO2, not just one or the other. It had to match both cases. And I've just highlighted in this green bar here just the overall range of what we consider to be a match for magmatic gases. So because all of our synthetic gases were, plausibly magmatic, and anything that was outside of that range was not plausibly magmatic, that gives us this really interesting result, because we see before and after the run-up and eruption, we have these sort of more quote-unquote magmatic signatures coming out of the volcano. During this run-up phase, we quickly drop out of, in terms of, I'm looking at the SO2-CO2 plot here, we quickly drop out of that magmatic zone, and then during the eruption overshoot it and fall back down. So we can make some interpretations about what that means. In this case, that's telling us that magmatic processes alone was not enough to account for this burst of sulfur that was released from the top. And instead, what we turn to, especially at Poas, is the hydrothermal system. And so this is a little schematic representation of what we think these data are telling us. What I'm showing you here, that blue blob at the top there is representing the lake, the water lake, and the red stuff coming from the bottom is sort of the magma and gases coming off of the magma at depth. And these green diamonds are showing you a hydrothermal system that's moving through the very shallow subsurface at POAS. And the idea is that we're seeing here in the SO2-CO2 data more and more influence from a hydrothermal system, where we've left the possible range where a magma could produce these gases. Again, this is in the run-up phase, and it's looking more and more strongly linked to a hydrothermal system. And that we're interpreting to mean the buildup of a hydrothermal seal. So the removal of gases from the system and reprecipitation as sulfur minerals, mostly within that sort of carapace below the lake. And then eventually, when the sulfur, the SO2 degassing at the surface got down to 0, that's the point at which we believe that the hydrothermal, that carapace was completely sealed, such that the pressure was able to really, really build up at that point, releasing catastrophically all of that sulfur that had been stored up in the hydrothermal seal. And so it's releasing all of this built up sulfur at once, which accounts for us overshooting our magmatic zone of gases there during the eruption. And then once that's done, you know, the hydrothermal system has been sort of blown up, literally, and we're back down to our magmatic degassing. So that, like I said, is sort of using this very specific example of ways that we can try and get creative with what little data we have, leveraging the power of really, really good field measurements and really, really good, you know, just decades and decades of thermodynamic experiments and thermodynamic tabulation to the point where we have these amazing thermodynamic databases to leverage with what data we do have coming in. Particularly data like surface gas data that's relatively easy, in quotes, relatively easy to obtain, as opposed to, say, petrologic data. You know, doing a petrologic study, first of all, is forensic. It's difficult to be predictive, but going up and picking up a rock, you know, sawing it open, taking a look, doing all the analyses takes a lot of time. It's easier to get real-time data about what's physically going on at the volcano. So those are the kind of data we want to be able to leverage, especially in cases like an observatory, where they need to be making quick, informed decisions about how to, for example, you know, work with stakeholders and policymakers in places where we have populations living near these volcanoes. And so what we can say then from this example is that we were able to determine that the 2017 eruption at POAS was an eruption that was triggered from the top down. So rather than being the influx of new magma, it was this formation of a hydrothermal carapace and then the rupturing of that carapace that caused this big eruption. And as for the gas modeling, my main takeaway points are that there's this need for a general model to quantitatively interpret these data. And this is just sort of an example of how we might start to think about approaching that. And also just to sort of, you know, throw a hat in the ring for thermodynamics, as it were, saying that, you know, thermodynamically based models are very versatile, and they show a lot of promise for these kinds of problems. So with that, I guess I'll take any questions that you guys have. Happy to talk to you about it.